Okay, today we're going to focus on the Sn2 mechanism. So this is pretty highly covered. Khan Academy does a pretty job, so if you're confused, go look at Khan Academy's video. I'm going to try and go for a little bit more complicated study of the Sn2 mechanism. So say we have a substrate like this, and say we react it in the presence of something like the cyanide anion. The actual Sn2 mechanism will proceed like this. The nucleophilic cyanide anion will attack the carbon bearing the leaving group, and in the same step as this bond forms, this bond will break. And as a result, our product formation will look like this. Alright, so arrow pushing is one thing, but actually understanding the chemical bonds and the interplay between these molecules goes a long way in informing your understanding about organic chemistry. So just like with the E2 video, let's look at what's happening with the chemical bonding. So once again, a sigma bond is formed for the overlap of two orbitals with the same phase along the same axis. So that will give you your sigma bond. Your antibond is the alignment of two orbitals out of phase along the same axis, which will give you this sigma star arrangement. Alright, once again, let's apply this to the original system that we are interested in. So let's look once more at our substrate molecule. So this time I've included the invisible hydrogens just for sake of simplicity when we start looking at the bonding. So, just like in the E2 video, let's take a look at this bond right here. So, this is where the sigma bond is located between the substrate and the leaving group. So, you'll remember that this carbon right here is sp3 hybridized. So, it has an sp3 hybrid orbital pointing out along here, and the chlorine is terminal, so it is non-hybrid. It has a p orbital pointing to the carbon's sp3. And when the overlap of these atomic orbitals gets you the sigma bond. And we'll note once again, this is filled, which means that there's electrons within this bond. Okay, once again, key point, when you create a sigma bond, you create a sigma antibond. Okay, and remember when we're always talking about bonds, we're talking about orbitals. So when we're talking about this antibond, it is going to be located in a very similar region of space. So once again, we have that sp3 hybridized carbon. This orbital is now combining out of phase with the p orbital on the chlorine. As a result, the antibonding orbital will be located here. Now, notice once more again, the sigma bond points from the carbon to the chlorine, and the highest density of the sigma antibonding orbital is located on the back side of this sigma bond. Okay, and the use of the word backside there is very, very intentional. So I'll say that once again. The sigma antibonding orbital is located on the backside of the electrophilic carbon. Okay, and just like before, we'll make the special note that this is empty. So the sigma molecular orbital, or the bonding orbital, is filled, and the sigma star antibonding orbital is empty. Okay, now once again I'll remind you of the way that this chemical bonding typically works. So, when you form a sigma bond, you form a sigma antibond as well. Because remember, a bond is just the same thing as an orbital. So you have a sigma orbital, bonding orbital, and you have an antibonding orbital. If you put electrons into the sigma bond, that's usually what you do, and the antibond is empty. But if you put electrons into the antibonding orbital, what happens is the overall bond order is 0, which means that there's really nothing holding the molecule together. So the key point here is that if you put electron density into the sigma star antibonding orbital, this will weaken the sigma bonding orbital. Well, what could possibly donate into the sigma antibonding orbital? Well, let's say here is our electrophile, once again, with the antibonding orbital drawn in, and here's our nucleophile, which has a lone pair located in this sp orbital, and then it has the ability to donate electron density into the antibonding orbital. What that will do is that will significantly weaken the sigma bond. Now, at this point, we have what is called a transition state. So as this nucleophile gets closer and closer to the electrophile, we enter the transition state, which is this. So here, these partial lines here, this dotted line means this is a partial bond, okay? So dotted line equals partial bond, because remember, in general, carbon cannot have more than 4 bonds to it. But in a transition state, that's possible because this is a partial bond and this is a partial bond. The nucleophile here is Cn, and here for us, the leaving group is Cl. So this transition state, if you remember back from general chemistry, you have a center with 5 bonds. This is called Trigonal Bipyramidal. Okay, so in Sn2, we have a trigonal bipyramidal transition state. And as this nucleophile comes in and donates electron density into the antibonding orbital, it weakens the sigma bonding orbital over here. So this bond between carbon and the leaving group weakens. As a result, you get your final product, which looks like this. Now remember, as the antibonding orbital is filled with electron density, that brings the bond order to 0, which means the sigma bond breaks, but immediately afterwards, you have a new sigma bond between carbon and the nucleophile. So it goes back to this filling diagram with this empty and this filled. Okay, that's a lot to take in. Let's try to summarize the facts we just learned from looking at these bonds. The first thing is that the Sn2 mechanism, like the E2 mechanism, is concerted. What that means is that bond breaking over here, bond breaking over here is happening in the same step that bond formation is happening. So this bond is being formed, this bond is being broken. That's happening at the same time. So let's write that down. Concerted means bond formation happens at the same time as bond breakage. The, ramifications of that are that the rate of this reaction depends on both the substrate and the nucleophile, because the rate determining step, there's only one step, is that initial attack of the nucleophile on the substrate, which depends on both the nucleophile and the substrate. That's why this is called Sn2, which stands for substitution second order. Once again, it's first order on the substrate, first order on the nucleophile. You add those exponents together and you get 2. Okay. Again, I said this in the other video, but I'll say it again. What it means when it's concerted is that our reaction coordinate our reaction coordinate diagram will look like this, supposing it's exothermic. So reactants over here, products over here. At this top, that's the transition state. Again, intermediates, isolable. Transition states, you can't. Okay. That said, let's move on to talking a little bit more, just like we did E2, about the ramifications of the bonding theory. So say we have an electrophile or a substrate that looks like this. You have the carbon bearing the chlorine with, well, 3 R groups, 1 alkyl group, 2 alkyl groups, 3 alkyl groups. You have a lot of steric bulk located at the electrophilic carbon. So if we add in all those invisible hydrogens, what we see is this. Now remember, as we were talking about before, the only way to reach that trigonal bipyramidal transition state is if this nucleophile is able to donate electron density into the antibonding orbital located here. Now I think I've made it rather obvious that when you have a lot of steric bulk around that electrophilic carbon, it makes it very difficult, even impossible, for this nucleophile to get in. So in this case, the Sn2 substitution reaction, or mechanism rather, cannot take place on this electrophile. And the reason is the ability of nucleophiles to reach this anti-bonding orbital is highly affected by sterics, not only here, but in the beta positions as well, so right nearby. Right, because as these groups are spinning around through space, they're basically repelling any nucleophiles that are trying to get close. So again, that's what I'm saying right there. Okay, and just like I said last time, I'd like to note that the reason that you cannot do an Sn2 mechanism on a tertiary carbon comes directly from this idea of bonding and antibonding and donation into the antibonding orbitals. So it's critical that you understand this bonding theory to being able to get a real good grasp of what's happening in this class. Okay, so let's take a look at an actual reaction. Let's get more concrete here and relate it to things that you actually care about. So, say we have an electrophilic substrate like this. We have a leaving group here, and we have sodium iodide in DMSO, which we consider a polar aprotic solvent. Don't worry so much about that. There'll be another video on solvents later. But what you should know from the past is that when you have something like sodium iodide that enters the solvent as a salt and immediately dissociates into ions. This iodine minus over here, this iodine anion, is pretty nucleophilic. Okay? So, do a bond rotation here, and we'll get the Cl facing downward. It might not seem very important for why I want to do that, but I want to illustrate that if we're going to do the arrow pushing here, what the actual transition state will look like. So say I have the iodine, it's a nucleophile, and it's going to be approaching the molecule at the back side. So again, the sigma bond from the carbon to the Cl is along here, so the antibonding orbital is going to be located here. That's where the nucleophile is going to attack. Doing that, the transition state, that trigonal bipyramidal transition state, will look like this. So this is entering, causing partial bond formation, and this is leaving, causing another partial bond to be broken. As a result, you get this as your final product. The Cl leaves, and the I is there remaining. And if you do the bond rotation back, you will see that the product looks like this, which tells you something very nice. Well, two things actually. Let's think about this for a bit. One, you'll notice that the Cl initially, the leaving group, was on a wedge, and now the incoming nucleophile is on a dash. We call this the Walden Inversion. Okay? And that basically means that there's an inversion at the electrophilic carbon where the attack takes place. Take a look at this animation here, and it'll be pretty clear. So here you see the trigonal bipyramidal transition state forming briefly at this point. But you also see what people call the umbrella basically being turned inside out. If we think of this as an umbrella, as this nucleophile comes in with its negatively charged electron cloud, it is pushing each of these bonds backward in space. This is what we're talking about when we're talking about the Walden inversion, the pushing of these groups from one side of the molecule to the other. And that's really what's driving this inversion that you're seeing. Okay? So back here, the reason why Cl is wedged and iodine is dashed is because of that Walden inversion. And now that you know that this is pretty much your shortcut, that if you're going to do an Sn2 reaction and your leaving group is on a wedge or a dash, the product is going to be the opposite. Now, if you're going to look at the chirality at this point, you'll notice that this, I guess the IUPAC name for this is R2 chlorobutane, so this is R. And over here, on the product side, this is S. Okay? So often, but not always, you'll have R to S or S to R when doing a Walden inversion. Now this is a very common misconception that you will always go from R to S or S to R, so let's try to clear that up. Okay, so suppose we have this kind of molecule. So again, this carbon right here, the one that we're interested in, this is a chiral carbon. The other thing that you're probably wondering is what D is. So D is deuterium. This is an isotope of hydrogen. Okay, and say we are using a reagent you probably haven't learned of yet called lithium aluminum hydride. So this guy, don't worry about him too much now. I'm just using him as an illustrative example. So lithium aluminum hydride, the only thing you need to know is a hydride donor. So if we're going to draw the Sn2 mechanism, we're pretty much going to pretend that we have a hydride. So as this hydride attacks here and does the Sn2 reaction, remember here's our leaving group, so here's the anti-bonding orbital, it's going to attack there. What you'll see is this kind of transition state as the H comes in as a nucleophile, because it's a hydride, and the Br starts to leave. Once again, trigonal bipyramidal, and the product will be this. I'll put that up here. Okay, so this was an Sn2 reaction. We had a Walden inversion. So what I'll tell you from ChemDraw is the name of this is R2 bromobutane 2D. Don't worry about the nomenclature, that doesn't matter. What matters is the fact that this is designated R. But after, the product is also designated R. So the point I'm trying to make is the same point I was trying to make up here. Walden inversion often goes from R to S or SR, but does not always go. Okay? The reason you see this kind of issue is because remember back to our way of assigning R and S. These are based on Kohn-Ingold prelog rules, which are based upon the atomic numbers of the things that are involved, which literally can change based on the nucleophile and the leaving group. So the reason why you could go from R to R or SS and doing Sn2 is because these Kohn-Ingold prelog rules don't reflect reality. They are a nomenclature convention. Okay? So typically you'll get R to S, but you won't always get R to S or S to R. So you should always check the chirality rather than just assume it's going from R to S or S to R. Okay, so whoops. Let's just pretend that wasn't up there for a second. Okay, so I want you to use this as your electrophile and this as your reagent. And I want you to pause the video and predict the products. Okay, I'm going to assume you give it a try. So this is sodium azide, which on exams you'll pretty much see treated as this when it breaks up in solution. So you don't actually need to know what it looks like. If you actually care what it looks like this. And the lone pairs are located on these outer ones. So there's actually minus, plus, minus. And since you have two minuses and a plus, the overall net charge is going to be negative. So that will do the nucleophilic attack at this location, which you don't have to worry about because it's a secondary carbon, and as the bond forms, this bond will break. As a result, your final product will look like this. Okay, let's look at another example. So this one should be near and dear to your heart because you saw it a lot last chapter. So take 2 or 3 minutes and try this problem. Alright, I'm going to assume you gave it a try. So the first step is that, once again, this will dissociate in solution to Na plus and NH2 minus, which will also have lone pair, which will do a deprotonation on this. What that will do is give you the negatively charged carbyl carbanion, which will look like this. Now this is a pretty good nucleophile, and this will do the attack on this, because that's primary, very rapid Sn2 attack there. So as a result, your final product will be what you've used in synthesis probably several times. It will be this. Okay, let's look at this reaction. So take 2 minutes, pause the video, try this one for yourself. Okay, so here the problem is that the electrophilic carbon is tertiary. And now you know, because of the bonding argument, that Sn2 can't occur on tertiary carbons. It can occur very quickly on primary carbons. It could occur on secondary carbons more slowly, but it cannot occur on a tertiary carbon. So this will be a no reaction through an Sn2 pathway, but there are other possible mechanisms that this can undergo, which we're not going to talk about in this video. Probably the next video. Okay, let's consider this one. So give this one a try for 1 or 2 minutes and see where it gets you. Okay, this one's tricky. I'll guide you through it. So what will actually happen is no reaction, or what should happen is no reaction. Okay, and the big question is why? What's different about this than everything else we've looked at so far? Well, suppose we draw the mechanism. So we have the nucleophile attack here. This is secondary, so that's fine. And the leaving group is iodine, so that backs out just like that. Which will go to this. Okay. Well, what's the problem? Well, the problem is that what's stopping the iodine from coming back and doing the nucleophilic attack like this, which will result in this kind of shenanigans happening. The problem here is that in polar aprotic solvent, I- is a better nucleophile than Cl-. So what that means is that the equilibrium will be farly pushed in this direction, because every time I comes off, it'll immediately get back on. In most cases, it'll actually beat the Cl. So again, this case, I is a better nucleophile than Cl, so the reaction will be stuck at reactants. It won't actually go to products. Well, sort of. So you can change this in a few ways. One, play with concentrations. So as long as the iodine is somehow trapped or kept in a low concentration, it won't actually be able to overtake the Cl. If the Cl is in mad excess, you could probably push the reaction forward to go in the way you want. The other thing is, and we'll get to this in a later video, what if we change it to a polar aprotic solvent? Some of you that know, the nucleophile strengths of the halogens, of the halides, changes in the solvent. So polar aprotic, iodine's the best nucleophile. In polar aprotic, F-, I believe, is the best nucleophile. So I'll talk again about solvents later, so don't worry about that too much right now. Okay, so let's talk about a few exceptions and tricky cases that someone should tell you about. So the first one is called the intramolecular Sn2. One instance of this reaction is in so-called epoxide formation. So what happens is that you have the NaOH, and the NaOH can then deprotonate this oxygen. Well, now that this oxygen is on the dash and this is on the wedge, it's possible for an Sn2 attack to occur like this. which is sort of unintuitive. And if you follow the mechanism for that, your product will look like this. Okay? So look into this more. I'm just making you aware that this is something that could happen. The other thing that you should be aware of is very similar, is this. So again, we have NaOH. One of the pathways that it could get through, there's multiple different reaction pathways that occur, is just like in the above. We can have the base do a deprotonation on this alcohol, making this nucleophilic. Now I'm going to number this 1, 2, 3, 4, 5, 6. So it's possible now that this has been made nucleophilic, this could attack this carbon and do what's called an intramolecular Sn2 reaction at this location, which will generate this. Well, let me try that again. Will generate this as your final product. And I'll tell you that in general, this will happen if 5 or 6 membered ring is possible. So remember, 5 or 6 membered rings are pretty much strainless, so if this can happen, it will happen. And the last one that I'd like to mention that maybe you haven't got to yet in the course, maybe you'll get to this much later, so if you haven't seen this in your lecture notes, don't worry about it right now, is the so-called Sn2 Primary Action. This one is perhaps the weirdest of all, and I'll just present the mechanism. You can have the nucleophilic, iodine in this case, actually attack this pi bond, which will cause these electrons to be pushed over here and eventually do a long-range ejection of that chlorine. The result is that the double bond is shifted over here, the iodine has added where the double bond was, and the Cl has been ejected. Again, this probably isn't on your exam, but be aware of this for the final.